Yeah. Okay, so I am starting this session by introducing myself. I am Oinak Ghoshal. I am a PMRF at Indian Institute of Science, Education and Technology, Kolkata, either Kolkata, and I have been assigned as a TA for this course, which is entitled as Fundamentals of Spectroscopy, and the instructors were Professor Shan Bakshi and Professor Anirban Hajra. And in this is the assignment related question regarding week number 10. Just a minute. Yeah. So this is the question. This is regarding assignment of week number 10, where I am going to discuss some questions regarding the topic that was discussed in this week, and also I am going to give you some hint how to solve problems regarding that, and this will be beneficial for you to solve problems regarding this, which will be given to you as an assignment. And so, in the basic idea about some of previous week's assignment, in the previous week, I was discussing about Raman spectroscopy, and three lectures were there for regarding two lectures were there for regarding Raman spectroscopy, and three lectures were regarding two lectures were regarding resonance spectroscopy. Okay. So basically, we have started looking at the shapes of this polarizability ellipsoid for different types of molecule, like for spherical top, symmetric top, asymmetric top molecule, and for water, it was shown that all IR active modes are Raman active. But for CO2, it was shown that IR active modes are Raman inactive and vice versa. Also, that means IR inactive modes they are Raman active. Okay. So the main difference comes from carbon dioxide and water structure. Okay, it was also discussed that, and you know, carbon dioxide structure is C double bond O double bond O, and for water structure is like this. Okay, so this the difference main difference here is that carbon dioxide is a centrosymmetric molecule. That is, it has center of symmetry. Okay, so in this case, it will follow mutual exclusion principle. And that means, what is the mutual exclusion principle? That means your Raman active modes will be IR inactive, and IR inactive modes will be Raman active. Okay. So this was mutual exclusion principle. There was some discussion about that. But in case of water, you cannot see any kind of center of symmetry. That's why water will not show this mutual rule of mutual exclusion. Okay. And from this, it was discussed that from this rule of mutual exclusion, you can easily find out the structure of any molecule. Okay. Suppose in case of NO2, this is a molecule. So it can take two different conformation. Okay. Either of this conformation, is this the conformation or this is the conformation. That means that what is the difference? The central atom is different in both the cases. Okay. In one case there is nitrogen central atom, and in another case there is oxygen is the central atom. Okay. So from the rule of mutual exclusion, or by just looking the IR and NMS IR sorry IR and Raman spectra, you can easily demonstrate which will be the following probable structure. Okay. So the main difference you can see in these two structures is that the first one has center of symmetry, or in some books it is written as centrosymmetric molecule. Let us see. Okay. So since it will have a center of symmetry, so as I have stated that for any centrosymmetric molecule, the rule of mutual exclusion will be followed. So if you are just following the IR active modes and Raman active modes, and if you see that if IR active modes are Raman inactive, or Raman active modes are IR active, so from that you can easily conclude that whether the structure is centrosymmetric or not. And if this structure follows the rule of mutual exclusion, then you can easily say that yes, nitrogen is a central atom, right? So this is experimental basis for the rule of mutual exclusion. And then there was selection rule for rotational vibrational transition. Okay, there was rule regarding rotational vibrational Raman transition. Okay, what was the selection rule? The selection rule, it was stated that for just the vibrational one, the selection rule was followed as is plus minus 1, plus minus 2, plus minus 3 or so. Okay. But for rotation, since it is involved, and you know in Raman the rotational selection rule is delta is equal to plus minus 2. Okay. So keeping in mind this delta G equals to plus minus 2 and delta V equals to 1, 2, 3 plus minus 1, 2, 3, anything would be, this was selected as a selection rule for rotational vibrational transition. Okay. And using this rule, the appearance of three different types of branches were observed: a Q branch, S branch, and O branch. Okay, and what should be the corresponding line with respect to nu I? That is, it was just, if you can remember the cases where I have discussed about P branch, Q branch, and R branch, you can see that for delta J is equal to plus 2, one branch is coming; for delta J equal to minus 2, another branch is coming; and Q branch is coming delta J equal to 0. Okay, so using that conclusion, you can easily say that in which direction the Stokes line will be shifted. Okay. Next, there was a discussion completely different from Raman. I mean, not completely different. It is related to Raman. There was a discussion on plane polarized light. Okay, and from there, plane. What is plane polarized light? The light which is coming, which the molecule faces. Actually, it is polarized in every direction. Okay. So from that, you are just choosing one kind of light, single axis polarized light. Okay, and from that, degree of polarization can be calculated. It is calculated as degree of polarization rho, which is defined as I perpendicular by I parallel. And it was shown that the range of this was from 0, its minimum value could be 0 and maximum value could be 1. So its range is from 0 to 1. Okay. And if this rho is greater than 0.75, then it is called that the Raman lines are polarized. Okay. And if it is not polarized, then delta value you will get, rho value you will get will be less than 0.75. This is just a statement. Okay. Then the interaction of matter with the magnetic field of light, it was discussed, and there was a complete movement from this Raman spectroscopy. There is a starting of resonance spectroscopy, which we will talk about one part of the resonance spectroscopy. And it was first the expression of the matter interaction with the magnetic field of light, and from that expression of the spin angular momentum was given. Okay, spin angular momentum. Fine. So spin angular momentum, what is the formula? The spin angular momentum is actually described in terms of mu s, and mu s can be defined as gs into E by 2 mu into capital S. Okay. And from that, you know the relation between angular momentum S and it was discussed already. And also the relation between gyromagnetic ratio and Bohr magneton, it was also shown. And Bohr magneton was discussed in this term with H cross, it was also depicted as Bohr magneton. And it was shown that G0 into D0 into Bohr magneton beta is equals to gamma into H cross. This is the relation between gyromagnetic ratio and this beta. Okay, Bohr magneton. And it was shown that the angular momentum vector, this is if it is polarized in it is in three direction. It was shown that the j direction, if magnetic field, supposing that magnetic field is in the z direction, if it was shown that the jg is constant, but jx and jy actually changes. Okay, but it was shown also that jx square plus jy square, if you squared it up and then added it, it will be constant. And so if j square, which is nothing but the summation of all these three squares, jx square plus jy square plus jg square, these three square will be constant. And so it was confirmed from here that j square and jz, these two will be constant. And it was shown that since they are constant, so jx and jy was discussed in the form of trigonometric functions. Then there was a discussion that omega, it can be related to this gyromagnetic ratio gamma with by this relation omega equal to gamma into b. Okay, so this precision, omega, this frequency omega, it is called Larmor precision frequency. Okay, and then there was a designation of this alpha and beta spin in terms of s and ms value. So alpha spin is regarded to ms value of plus half, and beta spin is related to ms value of minus half. You can just remember it for the rest of your life if you are going through the spin statistics. Okay, so alpha spin is corresponds to plus half spin and beta spin corresponds to minus half spin. Then the nuclear spin in terms of number of protons and neutrons. It was also said that whether the nucleus spin will be zero or it will be an integer or it will be a fraction, what should be. So it was discussed that what number of protons and what number of neutrons we have. Following that, you can easily tell that what should be the spin nuclear that is I. Okay, nuclear spin. Okay. Then there was a discussion that just like in case of earlier we have seen for rotational cases that when electric field interacts, the degeneracy is broken and the energy levels get separated. We have discussed that in terms of Stark effect. Okay, but here when but the same thing is happening that the magnetically degenerate levels which are this the degeneracy is afflicted in presence of external magnetic field. Okay, and this is called Zeeman effect. Okay, and how demand affect what will be the difference of between these two states, that was also discussed. And from this conclusion, it was shown that two processes are involved. One is nuclear process where nuclear spin is involved, and another is the electron spin. Okay, and based on that, these two different things in this atom, two different spectroscopy techniques were developed. One is for using nuclear spin. This is developed as NMR, nuclear magnetic resonance spectroscopy, and using this electron, another spectroscopy was developed which is known as ESR, electron spin resonance, or the EPR also you will know it, electron paramagnetic resonance, whichever it is. Okay, so it was the discussion of the previous week that I have discussed about all this, and there I have given a brief idea about the resonance spectroscopy. So in this week, what we are going to do, we are going to do one of these two, and next week I will discuss about ESR spectroscopy. But this week I will mainly focus on NMR spectroscopy, which is very much important tool for someone who is going to pursue his career in chemistry. Okay, so before going to that, let's check. Yeah, yeah. Okay. So now I am coming to this week's content. Okay. So this week's content mainly based on NMR spectroscopy. So this is lecture number 47, in which there was a discussion of alpha and beta spin states for proton and electron. Okay. So yeah. So there was a discussion of alpha and beta spin states for proton and electron. Okay. So as far I remember, the energy expression E that we have got is nothing but I can write this value I have with me as minus gamma B H cross into mj. Okay, this was energy expression. If you put Hamiltonian of the Hamiltonian, and then if you get the energy will come like this. Okay, so this will be the energy. Okay, so I think I should have taken another new page that will be very beneficial for you also, because too many discussions we have here. Questions are very much easy, but you need to understand the concept. Okay, so first of all, I am going to explain that if you have seen there that yes, so here using the Hamiltonian and Schrodinger equation if solved, H psi equals to E psi, you will get the energy. Okay, the energy came out. I have the expression is done there, and I have just expression with me. What I have written there is minus gamma B H cross into mj. So you know mj is the what is the you need to know all this term. Okay, this is called gyromagnetic ratio. This is different for electron and this is different for uh, nucleus or proton, anything. Okay, so this is the magnetic field. H cross, you know it, Planck's constant divided by 2 pi. And this, what is this mj? This is the magnetic quantum number. What are the magnetic quantum numbers? For alpha it is plus half, and for beta it is minus half. What I have said you earlier, that for the rest of your life you need to remember this, that for alpha the spin is plus half, and for my beta the spin is minus half. Okay. Now you got this energy. Now I have to find four different energy. Okay. So I'm just separating this part. One part is here. Suppose this part is for nucleus or proton, whatever it is. Okay. And another part is for electron. Okay. So E of, suppose for this nuclear case, E of alpha, suppose E of alpha state will be minus gamma of nucleus into beta B, sorry, this is B into H cross, and you know it is mj for alpha is half, so negative sign will be there. So I can write it minus half gamma n beta H cross. Okay. Similarly, energy of this beta state I can write as minus gamma n beta, sorry B, sorry I'm not, this is not B beta, it is B H cross into this half that was in case of alpha. In case of beta this will be minus half. Okay. So you can see the spin will be 1 by 2, the negative negative will be giving you positive sign, gamma n beta B, then beta I'm telling H cross. Okay. So by this way you can also find the energy of this alpha state and beta state of electron. The same thing will be there. This alpha state energy will be this one into omega gamma E, which is gyratory ratio of electron B into H cross. Okay. And E of beta will be half gamma E beta B into H cross. Okay. So we have got four different values corresponding to alpha state and beta state, and also for corresponding to nuclears and electron. Okay. So from that I just need to emphasize one thing. Now it is known that B is equals to positive. Okay. So yeah, this is the full magnet alpha. Sorry, this is beta. Yes. So saying is right. This is Bohr magnet. I'm sorry. Yeah, in each case it will be beta. Okay, so don't confuse this beta with this one. This is spin beta, this is the Bohr magneton. Okay, so beta, I can provide you this information that this beta is negative for electron and this is positive for proton or nucleus. Okay, so for electron, beta state is beta value is negative, and for electron, beta is positive. Okay. Now, can you tell me which level will be lower of energy between alpha and beta in case of this one? And in case of this one, which should be the lowest in energy? Alpha or beta? Can you tell me?
Both will be same.
I mean, alpha and beta will be same.
Yes, I think so.
Okay. But the signs are opposite. Okay.
Okay.
Yeah. So you can see here this A alpha, in this A alpha expression there is minus half mu n beta h. Okay. So if beta is negative, then E alpha will be positive.
The higher energy.
Yes, it will be positive. If beta
Okay.
is negative, this is negative. There is a negative sign in there, so this will
So
give
that,
the positive.
okay. So that the alpha is the highest energy.
No, first let me find his beta. You
Okay.
understand? Yes, yes, that you have what you have said is right.
Okay.
So
Thank
beta is of negative.
sign.
Sorry. Here this is positive. Okay. Sorry. Sorry. This is positive here. So if beta is positive, so E alpha is negative here, right?
Yes.
Yes. Yes. Yes. Sorry. Yeah. So if beta is positive, though E alpha is negative, and if
Yes.
beta here is beta is positive, so it will be positive.
Beta, beta.
Beta, yeah. So this EB will be positive, E beta will be positive, and E alpha will be negative.
Negative. So
So since
beta was
alpha
the
is yes,
highest energy. I'm right?
yes, yes, E beta will have
Oh,
higher energy than the E
okay.
alpha. So here, in case of nucleus, E alpha will have lower energy and E beta will have higher energy.
Higher energy. Okay.
Yes. Okay. Now
Okay.
in case of electron, you can see here that beta is negative here in case of electron.
Yes.
Okay. So in case this case, E alpha, which is also there, is a negative, and since beta will be negative, so it will be positive.
Okay.
Similarly, beta, if you put beta negative, this term will be negative.
Okay.
So similarly, here E alpha will be of higher energy because of it is positive value, and E beta will be of lower energy because it is negative value.
Negative.
Right?
Okay.
Yeah.
Yes.
So this is the main difference between nucleus and electron spin resonance. That is, in case of nucleus, the alpha state has a lower energy than the beta state, and in case of electron, the alpha state has lower, beta state has lower energy than the alpha state. And that is
Okay.
the discussion that was I am talking about for electron alpha spin and beta spin states for electron. And also, it was shown that the degeneracy of a state is given by the nucleus. Now I am just moving towards the nucleus one, and it was
Okay.
shown that for the objective of this degeneracy happens, and degeneracy was given by this relation 2I plus 1. So I, this part is called nucleus spin. Okay. So nucleus spin, how you can get this nucleus spin? This was also discussed that you need to see how much number of electron and proton are there in this molecule. Okay. So if you give for different combination, different types of spin will be there. Okay. And from that, if suppose if it is half, then your degeneracy will be 2 into half plus 1. This will be 2. Okay. So this the uplifting of degeneracy actually happens for MY level in presence of magnetic field, and this is called Zeeman effect. That's the one I am was discussing in the previous case. This uplifting of this degeneracy, which is known as in presence of magnetic field, it is known as Zeeman effect. Okay. Now the same thing if happens that the rotational energy levels in case of rotation I have also discussed that in case of rotational energy levels it is seen that the equal energy levels they are separated in presence of electric field. So the expression the effect is same but the name is different. The name is Stark effect. Okay. The same thing is there but the fields are different. Now the energy difference between two successive levels and also the selection rule that was also discussed. Okay. So I'm going to again to this one. So the energy you can find it if considering the degeneracy. So your delta E it will be Gn. Suppose for nucleus case I am just omitting electron for this week. Okay, for next week I will come with the electron. For this week, suppose just
Okay.
consider this nucleus. So this is Gn beta n into B. Okay. So the total energy, this energy difference will be this one. And the selection rule which will come, this was also discussed in the lecture that it will be plus minus 1, right? So from this, yeah. So energy rule difference and the selection rule that was also discussed here, and then it was discussed a formula regarding this was given that the radio frequency it was shown that for NMR you need the radio frequency, and radio frequency is related by this relation Gn beta n into B by H cos. Sorry, H. Okay. So this one Gn beta n B by H. Now you can see you can record whenever you are going to measure a NMR spectrum, you can either vary B or you can either vary this radio frequency. Okay. So mainly the initial discussions will be based on the variation of this B, considering this radio frequency is fixed. Okay. And then it was shown that the calculation of these units of this all the things, yeah, calculation of the units of this B magnetic field, and you know magnetic field unit is Tesla. Okay. Then the unit of mu, this is Tesla. Tesla. Okay. And the unit of mu, you know, this magnetic moment, it is I into A. So what is the unit of I? I is ampere, right? And A is the area. Okay. So meter square, ampere into meter square, right? And also it has another unit in terms of energy. You can find it as joule per Tesla. Fine. And the unit of Bohr magneton, it was shown that it will have same unit as mu because it is related to mu by the term this magnetic spin will be there only. So since they don't have any unit, so it will follow the unit of mu. And then if you the unit of mu, that is the joule per Tesla. Okay, I'm just writing joule per Tesla. And then you can get easily the unit of gamma, what Professor Sandberg has also discussed, that this unit of gamma will be, what will be the unit of gamma? Now unit of gamma will be, you know, this is the relation beta n equal to gamma n into h. Okay. So since gyromagnetic ratio have no unit, so so the unit of this gamma, it will be unit of beta by h cross. Okay. So you can write it in beta n by h into 2 pi. So unit of beta n here it is written as joule per Tesla. Okay. Joule Tesla inverse divided by what is the unit of J? Joule into J h 2 pi. This will be radian per second. Okay. So this joule will cancel out. So here its unit will be Tesla inverse radian. Yeah. So this unit will be radian second inverse. Right. So this is the unit of this gamma. So this was the discussion regarding in the lecture of 47, that the basic description of this all the terms, and also how the degeneracy is broken, and how many ways you can actually measure this NMR spectrum. And in the next one, there was the concept of this interaction of the magnetic field of light with magnetic moment of spinning nucleus, and also it was shown that NMR activity of this nucleus of C12 CO 16O etc. So in case of this one, you can see this I equal to 0. Okay. And so I equal to 0, you know, this mu in the magnetic moment is 0. Since magnetic moment is 0, that means this magnetic moment will not interact with the external magnetic field. Okay. Since they cannot interact, so they will not show any NMR signal. So they are actually NMR inactive. We will see 16, they are actually NMR inactive. Okay. Next, the reason was explained that for why NMR experiments are done in presence of high magnetic field. So what was the reason? Actually, it was shown. I need to go to the next slide. Yeah. So here the discussion about the population of this alpha and beta level, and it was shown that this ratio where n alpha and n beta denotes actually the population of alpha state and beta state. It is can be written as Gn beta n into B divided by 2 kt. This was the expression. This was derived using Boltzmann distribution, and from that it was discussed that in alpha minus n beta by this can be written as n total. So I can write it as Gn beta n B by 2 kt. Okay. So this is the expression of n alpha minus n beta by n total in terms of this one. And also there is some prior a priori knowledge was that in this case beta n is small. Okay. Beta nucleus is small, right? So since beta nucleus is small, so what about this term? This total term will get smaller. Okay. So this was only the part that can affect this part, and this is itself is small. So so it is since beta is small, so this part except b, of course I am just writing b outside. This part is actually small. Okay. So since these are small, so you can see the difference between alpha and beta state is small. So what does it mean actually? That n alpha minus n beta, this is small. That means the population difference between two successive levels is small. That means they are almost equally populated, right? Suppose in my ground state I have 10 molecules in alpha state. Okay. So suppose I have 10 molecules in the alpha state. So now and 9 molecules will be in the beta state. Okay. So that then difference will be very small. Okay. That means the both of them will be equally populated. You can see here that these are almost equally populated. So in alpha and in beta, these two states will be equally populated. Okay, fine. But to get a signal, you need what? A transition, right? So if two states, suppose I have two states which are equally populated, I cannot get it. So somehow I need to increase this difference, the difference between n alpha and n beta state. Okay. Suppose I am doing this in low, temperature is constant, Kb is constant, this is and very small. So I have only choice of this B. What is B? B is the magnetic field. Okay. So since I cannot vary the initial parts, these four parts I cannot vary, so I can only vary this B. So if I increase B, what will happen? If I increase B, this part will be sufficient enough, and in the difference between alpha and beta states will be sufficient. Okay, so that's why you can see if you are going any NMR measurement, you can see there is 400 megahertz, 500 megahertz, different kind of NMR equipments. Okay, so the magnetic field will need to be high to create a population difference between two successive states. Okay, that's why all the NMR experiments are done at very high magnetic field. Okay. Next, there was a condition of saturation. This was explained using Einstein B coefficient. So Einstein, why Einstein B coefficient? So this was done using Einstein B coefficient. And because why Einstein B coefficient was used? Because it was seen that Einstein A coefficient has much low value or almost negligible with respect to B. So Einstein B coefficient was used, and the net absorption rate of from any alpha state to beta state, the absorption rate, this was discussed in terms of B rho of nu into n alpha minus n beta. And this B is not here magnetic field. Okay. So this B is called Einstein B coefficient. Using this Einstein coefficient, B coefficient, you can easily tell the saturation condition or under which condition the difference will be maximum. Okay. And then the relaxation conditions, two relaxation conditions were there. That is, the magnetic field could be parallel or it could be perpendicular. Okay, to the external magnetic field. So magnetic field of nucleus, if this is parallel, then it will interact and it will deviate from this equilibrium position. And when it will relax back, this relaxation will be manifested by lattice which are present in the molecule. So this is also called longitudinal relaxation, and this is also known as spin lattice relaxation. Okay, and if this is perpendicular, then the energy will not change, but the entropy will change. Okay, and whenever this will be a change, when it will come back to its equilibrium position, then the relaxation will be manifested via spin. So this is also known as spin relaxation. Okay, and this transverse spin relaxation, this is actually occurs in the time scale which is actually also known as T2, and this time scale is actually designated as T1. Okay, so this time scale T2 has a very big role. It is actually responsible for the weight of the spectral line. Less the T2, as the value of T2 is small, more broader will be the peak. Okay, so in this with discussion, there was a discussion on why NMR samples are done in a high magnetic field, and also why which are NMR inactive nuclei. Also, how the saturation condition can be reached using Einstein decomposition, that was also discussed. And two different directional conditions are discussed about, that is one longitudinal relaxation and transverse or spin relaxation. In the next lecture, there was a discussion of the selection rule. Okay. So in case of this one, in case of NMR, two selection rules are there. Okay. So you know about this second selection rule at first. What I have told you in the next slide, that is second selection rule, delta m is equal to plus minus 1. So there will be a change in the magnetic number, or what do you say? There will be a change in the spin states. Okay. So, and also the important condition is the magnetic field due to light, which must be perpendicular to the externally applied magnetic field. The magnetic field of due to the circular motion of electron. Okay, so this will create a magnetic field. This magnetic field will be perpendicular to the magnetic field of the externally applied magnetic field. Under this condition, NMR transition will only happen. Okay, and also this circular motion of electron actually creates a magnetic field. Okay, why this becomes important? Professor Sandbakshy has also explained this beautifully, that if that is not the case, then for any b value, for all the protons you will get the peak in the same position. Okay, but you don't experimentally you can't get that. Okay, so why are you not getting that? Because there is the motion of the circular motion of electrons, and this circular motion will create a magnetic field. What kind of magnetic field? Does it reinforce or does it shield? It actually shields. Okay. So this magnetic field, if I write it in terms of B of electric due to electronic motion, BEL, it is described as minus of sigma into B. And since it opposes, there is a minus sign, right? And this sigma is, it is known as shielding constant. Okay. And why this is very much important? Because if in a molecule, suppose you are doing some NMR of protons or 13C, etc. If you are going 13C or in 1H proton, you can see easily that there the pole the peaks corresponds to the hydrogens at different positions in the molecule. They are different. Why they are different? Because the electron density is not same in each hydrogen, right? Since electron density is not same, so the field that is experienced by the electrons or by the nucleus that is present there, or there is a hydrogen that is present there, this field is different due to different amount of shielding. Why different amount of shielding? Because different amount of electron density is present everywhere. Okay, so the field that is experienced is B minus sigma B. Okay, so I can write it as B into 1 minus sigma. So if sigma increases, then what will be the value of B? B will decrease, right? So if there is some circular motion of electron which is mainly opposing the external field, that means increasing the sigma, your B, the field that is experienced by the molecule or the atom, will decrease. Okay. So there was be a change of positions of peak due to this is called chemical dissimilarity. Okay. So this chemical dissimilarity actually drives different positions of the peak. Okay. So yeah. And if it was also very well explained using aldehyde hydrogen and proton hydrogen. Okay, suppose in case of I am writing suppose uh, yeah, CH3CHO. So here two protons are there. Okay, one is CH3, another is this one. Should they have the same frequency in the NMR? No. Why they will not have? Because you know this is electronegative element. Oxygen is an electronegative element. So it will pull electron density from here. So it will making it more delta plus. Okay. Since it will become more delta plus, so more electron density will be from hydrogen will be shifted towards this carbon. So hydrogen there will be very much less electron density. Understand this situation, then you will understand everything. Okay. Suppose I am writing it here. CH3. Okay, so H3C supports C double bond O and there is hydrogen. So my question is both the hydrogens will it face the same field or do will have the same delta value for these two hydrogens? No, this will not have the same value, right? Why? Why this will not have the same value? Because both are hydrogen. Why they don't have the same value? Because there is the oxygen atom. Okay, it is electronegative, so it will pull electron density towards oxygen. That makes this carbon delta positive. Since it becomes delta positive, electron density from the hydrogen will move toward this carbon. So electron density will be less around this one. Does it the same case with the methyl hydrogens? No, it will not be the same case. So for methyl hydrogen, you can see the carbon is directly attached with this carbon. Okay. So since this is delta positive, so it will pull electron density from here. Then it will pull from this hydrogen. So it will not face this carbon directly. So this hydrogen, three hydrogens and this hydrogen will not give the same thing in the NMR spectrum. Okay. So yeah. And it was shown finally that the difference between B2 and B1, B2 minus B1, I can write is by to divided by V2, it is nothing but sigma 2 minus sigma 1. What is sigma 2 and sigma 1? Sigma 2 and sigma 1 are the fields due to these two different protons. And you can see if you change this value of B, the sigma 2 and sigma 1, that is the difference will be changed. So we need to find something, some generalization for which is valid for every cases. That's why the next lecture will depict that. That is, in the lecture 50, there was a consideration of magnetic field of a standard substance. What I have discussed, what I have discussed here, that this B2 minus B1, okay, by B2 will be sigma 2 minus sigma 1. Okay, so you can see what we are doing. We are actually, if when we do by 1, okay, so we are what we are doing actually, we are just fixing this B1. Okay, we are fixing with the reference which has 0, which can be thought as TMS, tetramethylsilane, which is chosen as the standard substance. Okay, so from that formula to calculate delta H, and now this problem is fixed. So since there is no two magnetic fields are there, one magnetic field you know, so just putting just one magnetic field you can get this difference. The difference is devoid of any magnetic field. Okay, so the formula to calculate this chemical shift, this was also discussed. that this chemical shift can be explained as sigma h will be equals to B reference, okay, minus BH by B reference. Okay, and since they are coming in the unit of 10 to the power minus 6, so you need to multiply it with your 10 to the power 6. So it will give you some number. Okay, without this 10 to the power 6 times, this will only give you up 10 to the power. Suppose because why the magnetic field difference will be in some chains or something. Okay, and this magnetic field will be in megahertz. So 10 to the power 6 times. So if you go, it will become 10 to the power minus 6. So to cancel this 10 to the 6 times is multiplied here, and this sigma h is called chemical shift. Okay, and this is related to also if you have varied your magnetic field, if you have if you have static magnetic field, you have just changed the radiation, you can also get this relation. Sigma h will be replaced as nu of h minus nu of reference by nu of h into same thing into 6. Okay, and this is related also to sigma 2 minus sigma 1. Okay, so sigma 2, since you know sigma is for some 1, you can easily say that, right? So delta is related to the sigma, and then there was very easy discussion on a scale of tau. Tau scale can also be used. Tau scale is defined in whatever value you are getting from this delta. So whatever value you are getting as delta, you just put you just subtract it from 10, you will get the value of tau. Okay. Now the scales are you got the what are the magnetic field roles you got what is chemical shift, and now you have to find what is the value of chemical shift. So in just up to this, you just understand that for different hydrogen present in a molecule, you will get peaks at different positions. Okay, because for every gases the delta value or the chemical shift will be different. Now the factors on which chemical shift will depend. Okay, two factors are there. One is electronegativity, another is ring current. Okay, so just a minute. Yeah. So why is the electronegativity important? Because what do you mean by electronegativity? Electronegativity means a higher electronegative atom will pull the electron density towards itself. Okay, electronegativity means it will have more attraction towards electron. It will like to have electrons towards itself, right? So if someone suppose a proton is attached with some electronegative element, okay, so it will the electronegative element will take this electron density from this bond. So the hydrogens will have low electron density. And that what I have discussed that if you have lower electron density, then you will shield it very less. Okay, so if shielding is very less, so the shift will be called downward shift. That means higher del value. That's why you can see in case of acid, it will come carboxylic acid, it will come like 11 or 12. When the two oxygen atoms are there, they will all take this electron density, and this hydrogen will have very low electron density, right? And since you will have low electron density, so your delta value will be higher. So if electronegativity increases, delta value increases. Now the effect of ring current, you need to understand that this ring current. So whenever benzene ring is there, so benzene ring actually there is what is kind of benzene ring? Benzene ring like this, okay, planar, all electrons will be planar. So there will be electron density up and here, okay, here and here there will be electron density. Now whenever I am since electron is moving, so they are creating magnetic field. So magnetic field is coming like this, magnetic flux, okay. So you can see in this point is designated as B, and if this point I designate it as A, you see in B point the magnetic field is getting increased because the magnetic field is in this direction. Then this B at this B point, this will increase the magnetic field, but A point it will oppose the magnetic field because it is coming like this. Okay, suppose I am putting magnetic field like this. Okay, so yeah. Suppose I have magnetic field like this. So if there is magnetic flux like this one, okay, so they are coming like this one. So in this point, suppose I have stopped it here, it is moving like this one, this one, this one, this one, okay. So at any point, this point, what you can see, this magnetic field, you can see here, this magnetic field will be in the same direction. So the magnetic field will increase. And when this will come back like this, then you can see this will be in opposite direction. So this at this position, this will actually block this magnetic field. Okay. So by what is the implication of that? The delta values for different hydrogens at an aromatic carbon or aromatic benzene ring, this will be different. So that is I have written here that for aromatic molecules, NMR signals of different proton occurs at different position due to the effect of the ring current. What I have discussed here, the effect of the ring current. Okay. So for this ring current, in some position, the hydrogens which will feel more magnetic field, they will be it will feel more magnetic field, then this will be upshifted. Okay. So in the next lecture, there was a discussion that if you just make this NMR spectrum looks in a high resolution, you will see that all the peaks you are seeing as a single peak, they are actually divided. Okay. So for high resolution NMR spectrum, it is seen that fine structure are there. Okay. So a peak that you can see a single peak, it is actually divided into many categories. And then from that you can calculate this coupling constant J. Okay. So coupling constant due to spin coupling, what I have saying that the fine structures are obtained, and what is the coupling constant? The peaks difference you from this peak difference you can calculate. Okay. And also how many number of peaks you can observe? You can observe only peak number of n plus 1. What is n? You can observe peak of n plus 1. What is n? N is the number of hydrogens or n is the number of atoms which are completely different and which are neighborhood. Okay. So if there are three hydrogens, suppose I am taking the case of aldehyde. Okay. Suppose I am taking the case of aldehyde. This, how many of these hydrogens are there? Three hydrogens. Okay. And how many hydrogens is there? Here is only one hydrogen. So this three hydrogen will show 1 plus 1, that is 2. And this 2 in this language we will call as doublet. Okay. And what about this hydrogen? There is a 3 hydrogens nearby, right? So it will form a quartet. Why quartet? Because I have said the 3 different hydrogen are there. So 3 plus 1, so there will be 4 peaks. Okay. Now, what should be the intensity of the 4 peaks? Are the 4 peaks same or they are of equal different intensity? It is actually given in using Pascal's triangle. Okay. You have seen this Pascal's triangle. That is for this doublet, the spin will be 1 is to 1. The next one for 3, it will be 1 is to 2 is to 1. For this 4, this will be 1 is to 3 is to 3 is to 1. How this is calculated, you can see here. I am not going to discuss that. You can see in the lecture of Professor San Bakshi. And also, it was explained that for a nuclear spin of I, what should be the total number of signals? This was given by 2 and I plus 1. And tree diagram is just the same like just of this Pascal diagram. And it was shown for this compound CHD3CO CHD2, this ID for here is 1. So how the intensity of the peak will be there? Since the nuclear spin is completely changed, the peak will be changed. Okay. So for ID equals to 1, if you see the tree diagram, you can see the 5 peaks will be obtained. Okay. And these 5 peaks will have different intensity. Right. And the intensity will be 1 is to 2 is to 3 is to 2 is to 1. Okay. So this was all the discussions regarding the week's content of NMR spectroscopy was Professor Sandbakshi has discussed. Now I am going to the question. Okay. This is the first question that you have to choose the correct option. That NMR spectroscopy involves magnetic field, ESR spectroscopy involves electric field, IR spectroscopy involves electric field, and micro spectroscopy involves magnetic field. So I'm just coming for 1 or 2 minutes. Okay. Hello. Hello.
Yes, sir. So,
Yeah, sorry for the delay actually. So, what are you saying? Yes, so I'm going to solve some questions. Um, First question is, you have to choose the correct options from here. That first option is cinema spectroscopy involved magnetic field. ESR spectroscopy involves magnetic field. IR spectroscopy involved electric field, and microwave spectroscopy involves magnetic field. Okay. So this is the question. I'm going to solve it. So since no one is here, so I am just telling the answer. So you can find this in reference in for lecture number 47, that in ESR and in NMR spectroscopy, actually what happens between difference between this IR and NMR, actually where it is developed, actually that in ESR and NMR spectroscopy, magnetic field of light actually interacts with the matter. But for IR and microwave, it was shown that the electric field of light that is mainly involved. Okay. So in one case there is the magnetic field of light, okay, the magnetic field of light, Another case is the electric field. Okay, so in ESR and NMR, you have seen the degeneracy of the levels are broken in presence of magnetic field, and but in presence of IR and a microwave, the electric field is responsible for the breaking of these levels. Okay, so from these correct options, you can choose from this option that NMR spectroscopy involves magnetic field. This is correct, right? NMR spectroscopy will always involve magnetic field. ESR spectroscopy involve electric field. Yes. ESR spectroscopy, no. IR spectroscopy involved electric field. Yes. Microwave spectroscopy involve magnetic field. No, they will involve electric field. So this ESR and NMR, these two. Okay, so these two resonance spectroscopy implies with this magnetic field, and other IR and micro vibration and rotational spectroscopy, they are using actually electric field of light. So this is the correct answer, that NMR spectroscopy involves magnetic field, but IR spectroscopy involves electric field. Okay. So my next question is, why Bohr magneton is given by the mass of electron is given. So you can also find this answer in lecture number 45 or 47. What Professor Bakshi has explained it, that Bohr magneton actually given by beta equals to Eh by 4 pi m. How this is coming? This you can find in also details in lecture number 45, where there was the starting of this resonance spectroscopy, that this Bohr magneton, to explain this, I need to use this relation mu s or magnetic moment. Okay, this mu s can be written as Gs into E by 2me into s. Okay, and here it was explained that beta, that is Bohr magneton, Bohr Bohr magneton. So the Bohr magneton can be explained using beta. So beta is can be nothing like E h cross by 2me, right? Now you know this is the expression for beta, E h cross by 2me, what I have also discussed. Now in all these examples, there is no h cross term, so we need to convert it to h. So h cross is nothing but h by 2 pi. So m is the mass of the electron. So here it is no e mentioned, so I'm just writing it m. M is the mass of electron. In the question it is given you here. You can see here. Okay. So here it is given the mass of the electron is m. Now I'm coming to the point that the beta or Bohr magneton will be Eh by, sorry, there will be 2. Okay. This 2 will be there. 2 into m. The 2 into 4, so 4 pi m. So this is the value of beta Eh by 4 pi m. And you can see here the third option is correct here. Okay. So this is answer. Number 3 question, the angular momentum vector J precedes along the surface of a cone with the angular velocity of omega. So you have to find the expression of omega. Here symbols have usual meaning. So what I was actually discussing with you, that what should be the expression of omega. Okay. So you can also find it in lecture number 45 or 46. You can easily find that. And actually from this value of j, when j is preceded, it creates a cone, and from that cone you can get this omega. Okay, so for this j, angular momentum vector j, from j, this j, one easily can get that if jx can be considered as a cos theta or a cos omega t, and jy is considered as a sin omega t, from that you can easily again say that d2jx by dt2 is nothing but, if you go through it and just substituting it, you will get this one. Okay. d2 j2 d2 jy. Okay. So d2 j of y by dt2, it is nothing but if you go through it, it will also give you this one. Okay. So jy is also give you jy. Okay. Now we whole square jy. Now, if this is the convention, if you take this omega t thing, it will always come as minus of omega square into jx. This will also come as minus of omega square into jy. If you don't believe me, you can do that, right? And if I think you know this differential equation, so if you can just mix it and you can say omega equals to gamma into b. Okay. So this what is this omega? This omega is actually called Larmor precision. Okay. Larmor precision frequency. Okay, this is called Larmor precision frequency. So this is given by omega into p. So what is the relation? The relation is this one. Okay, so you can easily get this one as your answer. Okay, so from that you can easily say which is your Larmor frequency, omega equal to gamma into p. So next question I'm moving. So now nucleus spin quantum number of 12C is, this was also discussed in lecture number 46, that for a molecule for carbon 12C, 12C, what is the 12C number of, you can say that you have to find as I. Okay, okay, so I'm going step by step so you can understand that. So you have to find potency, what is the value of I, right? So for 12C, you know number of proton, how many number of protons will be there? Proton will be 6. How many number of electrons will be there? Electrons will be 6. So how many number of neutron will be there? Neutron will be 6 also. Okay. So you see here, if it will have 6 protons, 6 electrons, 6 neutrons, right? And we have discussed that for an atom which have even number of proton plus even number of neutron, this condition if it is satisfied, then its nucleus spin will be 0. Okay. So if some atoms, I suppose 16 oxygen, they like it will have 8 proton, 8 electron, 8 neutron, right? So in this case also you can see that it will have even number of protons and even number of neutrons, so you will give I equals to 0. Okay. So similar case here, 6 electron, 6 protons, so it will give 6 only 6 proton, 6 neutrons, so it will give I equal to 0. So the answer is 0. Okay. Now I'm moving to the next question. This identify the correct pair. This is a just statement based question. You can find also in lecture number 48 that relaxation from the saturation condition is possible in two different ways. Okay. So whenever the saturation condition is arising, two different ways you can just relax from it. One is spin relaxation. Okay, or transverse relaxation. Where is this the transverse relaxation? That is the magnetic field which is perpendicular. Okay. So if it is going to come to the equilibrium position, it will relax back by using spin. So it is known as spin relaxation. And another will be possible if there is the spin, the it will be coming via the lattice. Okay, relaxing the lattice. So it is also known as longitudinal relaxation. So you have to find the correct pair of for here. So transverse spin lattice, no, longitudinal spin. These two are wrong. So transverse is the spin and longitudinal is the spin lattice. So this is the correct answer. Okay, this transverse is the spin relaxation and longitudinal is the spin lattice relaxation. So I think we know already have joined it yet. Yeah. So following the delta NMR chemical shift, which will have highest positive value. So I have explained it times before that you can also find this answer in lecture number 50. That explanation is that when the electronegativity of the atom increases, the delta value of the increases as sigma decreases. To make this simpler, we just writing this x. Okay, I am just designating. You can see here that all the things are same, just atom are different. Okay, so I am writing it H3C X. Okay, so this X, what is this X? This is the halogen, right? So fluorine, chlorine, bromine, iodine, etc. Fine. So these are the halogen series, right? Now from this X, so from this consideration of this electronegativity, okay, from this electronegativity you can also get this NMR shift. Okay, and we have said that if electronegativity increases, if electronegativity increases, then what should happen? With the increase of this electronegativity, it will pull most of this electron density towards itself, right? It will pull most of the electron density towards itself. So the hydrogens will have will be shielded, more shielded or less shielded. This will be less shielded. Will be less shielded. And since hydrogens will be less shielded, so sigma will be low. So what I'm saying, if electronegativity of the atom increases, if electronegativity increases, so hydrogens will have be less shielded. Okay, since it will be less shielded, so electron density will be low, and this will oppose it low. It will oppose the field will very lowly. Okay, so since it will oppose its low, sigma will be low. So what will happen? There will be upfield or downfield shift. The shift will be downfield. Okay, so if sigma is high, that is more screening, there will be a upfield shift. And just remember, in case of NMR, the scale is oppositely directed. Okay, the scale is like this one, NMR scale. Okay, so and the scale bars will be like 0. This will be 0, 2, 4, 6, 8, 10, like that. Okay, so it is increasing towards the left. So this is downfield shift. That means what will be the value? So it is downfield shifting. That means it will have this one. Okay, so its value will be high. So in conclusion, we can say if electronegativity increases, then delta value increases. So this is the conclusion from here, that if electronegativity increases, then sigma decreases, then there will be some downfield shift. This is downfield shift, and downfield shift means this chemical shift delta will increase. So if electronegativity increases, delta increases. This is the final conclusion. Now you have to find among these four X which one have higher electronegativity: X, fluorine, chlorine, bromine, and iodine. You know, in the periodic table, FCl, Br, and I. Okay. So you see in the periodic table, as you going from upper to lower one. Okay. So fluorine has the highest electronegativity. So among the four halogen atoms, fluorine will have highest electronegativity. Since fluorine will have highest electronegativity, so it will have more positive delta value. So answer is CH3F. Okay. Yeah. So the next question is, so according to Pascal's triangle law, what should be the intensity ratio for n equals to 2? What should the ratio? So n equals to 2, n equals to 2. So how much peaks will be there? According to n plus 1 rule, number of peaks will be 3 peaks. Now I am just drawing Pascal's triangle. Okay, so this is from 1, this is 1 and 1, 1 to 1, 1, 2, 1, 3, 2, 2, 2, 1, 3, 1. This is 1, 3, 1, 4, 3, 3, 6, this is 4, this is 1. Okay. So we have to find that for which case you are talking about. So in use this case there is 3 peaks. So 3 peaks means the intensity will be, according to Pascal's triangle, the intensity will be this one. 1 is to 2 is to 1. So this is the answer. So the total number of peaks will be 3, 2 plus 1, 3. So that is will be 1 is to 2 is to 1, which is the answer. Right? So the next question is the G factor for 1H and 13C are 5.6 and 1.4 respectively. So for same value of magnetic field strength, if 1H resonate at 600, so 13C will be resonate at which one? Okay. So you can find this also answer in lecture number 49, which I am going to solve here now. But you need to know this relation that the new radio frequency, okay, it will be G mu B by H. Okay. So if B is same, I can write that nu 1 by nu 2, which will be equals to G1 by G2, right? Now I am for carbon and hydrogen I am writing, since I need to find this 1H resonance frequency, so I am writing hydrogen in the above. So by carbon is equals to, so will be Gc by Gh by Gc, because this is directly proportional. What is the Gga? Gh, that is gyromagnetic ratio or G factor of hydrogen, 5.6. What will be the value of that for one carbon? This is 1.4. So ratio will come at 4, right? So now, oh sorry, you have to find for carbon. So you just take it opposite, that will be equals to new hydrogen by 4. You can see that new carbon is equals to new hydrogen by 4. Now hydrogen resonate as which wavelength? 600 megahertz. That puts the value of 600. This will be divided by 4. So what will the value? 150 megahertz. So this is the answer, 150 megahertz. So if there is a ratio of the gyromagnetic ratio or the G factors, if one is response at resonates at 600 megahertz, then it is obvious that 13C will resonate at 150. Okay. So I'm moving to the next question, which states about the correct statement regarding shielding and chemical shift. Okay. So first is the larger screening means upfield shift, downfield shift corresponds to molar delta value, larger screening means downfield shift, and the greater the shield, less will be the local field. So this is a question. So you can also find this answer in the lecture 50. What I was mentioning, that larger screening, what does larger screening means? Okay. So I have discussed that due to motion of this electron, it will create a magnetic field, which is given by BEL is equals to minus of sigma into B. And also, I have told you that what is the significance of this negative sign. Negative sign implies that it will oppose this magnetic field. So the magnetic field that was actually experienced earlier by the molecules, this will actually change. So why how it will change? It will change by this amount B minus sigma B. Okay. So if you take common B, 1 minus sigma. Now if you put it in the value of nu will be Gn beta n to be 1 minus sigma by h. Okay. So B, which was earlier in the case of nu, it is converted to B into 1 minus sigma. So larger screening, that means which what does it that implied? Sigma is large, right? So larger it is screening means it is opposing the field is larger. That means higher. That means sigma is large. Since sigma is large, so here you can say one thing. Since sigma is large, so B into 1 minus sigma, it will be large or small? It will be small. So the molecule, the atom in there will experience less field compared to this one. Okay. So it will feel field of B into 1 minus sigma, right? So since it will feel less field, so the how much will what side will be shift? So it will have upfield shift, right? Okay. So upfield shift means I have told you that upfield is in our scale. This is from right to left. So upfield means it is going to the right. That means lower del value. Okay. So you can find the answer is here. The larger scanning means upfield condition, and also the greater is the field, the less will be the local field. Two things are also covered here. That larger scanning means upfield transition, and also the greater the field, the lowest will be the local field. Okay. So according to Pascal triangle intensity ratio or n equal to 3. I'm not gonna do this because I have shown you what is the Pascal triangle. So since n equal to 3 is here, so number of signals or number of peaks or intensity ratio, or better if you write the intensity ratio of the peaks. So how much peaks will be there? N plus 1. So 3 plus 1, that will be 4. So 4 peaks intensity ratio, if you go through this Pascal triangle, 1, 1, 1, 2, 1, 1, 3, 3, 1. So this is 1, 4, this 1, 4, 6, 4, 1, like that. Okay. So you can see 4 peaks are there. This corresponds to 5 peaks, and this corresponds to 4 peaks. So what is the ratio? 1, 3, 3, 1. So the intensity ratio you can find from here, that is 1 is to 3 is to 3 is to 1. Remember guys, when you are going to solve some problems regarding this, you are in the question you are given for n equal to 3. Don't confuse it that 3 peaks are there. N equal to 3 means that n plus 1 rule will be followed and 4 peaks will be there. The intensity ratio will follow 1 is to 3 is to 3 is to 1 pattern, right? So you can find in this selection number 51 also the answer that for n equal to 3, total number of peaks due to splitting will be 3 plus 1 is equal to 4, and the ratio will be 1 is to 3 is to 3 is to 1. So this is the correct answer. The last question is, which are the correct statements regarding NMR spectroscopy? This is the subject questions that for NMR Einstein A coefficient is much smaller than B coefficient. For NMR Einstein B coefficient is much smaller. Population of these two levels are almost same and energy gap between these levels is large. So you can find this reference in lecture number 48 that for NMR Einstein's A coefficient is much smaller than B coefficient. Okay, I have told you earlier that. Yeah. So Einstein's A coefficient is much smaller than B coefficient. Okay. So you can neglect this A coefficient with respect to B coefficient, and when we have discussed about the absorption rate, we have only considered this B coefficient of Einstein. Okay. Also, we have seen that the population difference. So among these two options, this Einstein's A coefficient is much smaller than B coefficient, right? And this population difference, I have also done a question among this. This in total, I have shown you this is nothing but equals to, what is this equals to? I need to the expression, this population difference. Just a minute. Yeah, Gn beta n B by 2 kt, right? So we have seen the population of upper level and lower level depends upon this factor, and for a given magnetic field for a given kt, this is very low. Beta low, value is less, which implies actually that in alpha minus in beta is negligible. Okay. What does it suggest? Because that this suggests that the difference between the population of these alpha and beta levels are negligible, are very very less. Okay. So is this same? So in the population of these two levels are almost same. And the last option is the energy gap between the Gman levels of nucleus is large. Is this true? No. The Gman level between is the difference between Gman level is large for electron. For nucleus, we have considered that beta is very less. Okay, and the value is given by Gn mu n beta. So since beta is less, so the gamma is less. That is the simple thing. You understand? Okay, so upon this, since beta is less, so this whole term will be less, and this will be less for nucleus. So that means for Zeeman effect in case of nucleus, the difference between two energy levels is less. So the answer is that for NMR, Einstein's A coefficient is very very much less than Einstein B coefficient, and also the population of upper and lower levels in NMR are almost same. Okay. So this is regarding questions of this week. So I have discussed all the questions, how I have solved it. You can understand it. I think we should understand it. And if you find any problem, you can comment in the. I will upload it in the YouTube, and you can comment there. You can ask me the questions. Okay. So I need to stop this recording. So session is complete here today.